Hi everybody. Sorry about that. I was just quickly trying to eat. Let me turn this off. Welcome back to Chem 131. Maya is here. Yes, I hear you. She's here in the hallway anyway. And wants everybody to do their best learning about alkenes. What can we talk about for administrivia? Let's see here. Last call for lab number 1. I'm going to send an announcement out after class at some point today. That basically just says, hey, lab 1 is due. Please turn it in by tonight. So do that. Make sure that you turn that in by the deadline. If you miss the deadline tonight, then you have to use your NQA coupon and turn it in. It has to be in by tonight. No exceptions. What else do we have? Quiz number 1 due Friday. Make sure you get that done too. That is the Friday deadline is a soft deadline. You'll have an extra day. How many questions do we expect on the quiz? I don't actually remember. I want to say it was like 11 or 12. Something like that. When we last left off, we were here. 14, is that how many it was? Okay, thank you. I know that it's 15 points. I think I had a bunch of 1-point questions and maybe some 2. "30 minutes is more than enough time. It's mostly multiple choice or arranging. If you know this stuff, you should be able to do this in 5 minutes. I give you 30. All right. We were discussing addition reactions this week. We left off last time by talking about what happens when we add H2 across the molecule and then X2, where X is ClBrI. F also works. Oh my goodness. Sorry, give me a second. Maya, what is wrong with you? Maya, stop. Why are you yelling in the background? Yeah, you don't know. Stop that. I didn't hit mute, did I? No. You hear me talking to my cat in the background. Maya, what? What do you want? Oh my goodness, she's just like this some mornings. I apologize for my needy cat. Alright, we studied these addition reactions. Today what we're going to study is HX, where X is still HCl, HBr, HI, HF, etc. We don't generally use HF, but just in case it comes up, it does follow these rules. When we add HX across a double bond, at first it looks like the exact same thing is happening. So I would make a bond here, break this bond, break this bond. And for a symmetrical molecule, this is true. So, for instance, our ethene molecule here is completely symmetrical. I can put the H on either side and I get the same result because I could spin this around like this, right? If there's only one X, it could be in any of those 6 positions where the H's are labeled. And I would get the same result because single bonds spin around. So this could go however it wants to. And all possible configurations would be equivalent. What if we did something like this, where the molecule is now no longer symmetrical? Which means that if I were to add HBr, if I put the H here in this position, it would be closer to the CH3, and the Br would be on the end. Or maybe the other opportunity, or the other arrangement occurs where instead the Br goes on the side with the CH3, and the H goes over here. Maybe both of them occur. Maybe it's random. What happens? And the only way to answer this question is to do the experiment and see what we observe. And so that's what we're going to do. So let's first draw out the two possibilities. I'm going to circle the groups that I have added here in both cases. So something must happen here, and that something must be either I get the top case only, I get the bottom case only, or I get both. If I got neither, we wouldn't be bringing this up. So that case is already being crossed out. And it turns out that as much as we want to say, oh, it probably forms both, that's not the case. It turns out only one of these products form. And the way that we determine which product forms is by using this rule called Markovnikov's rule. Markovnikov's rule says when you add HX across a double bond, you put the H where there are already more H's. Okay? So what that means is that if I'm going to add HBr to this molecule right here, I have to look at which side connected to my carbons here. And notice that I'm only circling adjacent atoms here. So I have this C and this H, which is bonded to this carbon here. And on this carbon here, I have this H and this H, okay? I don't care about atoms that are further away. I only care about H's that are already bonded to that atom. So on the left here, I have one H. On the right, I have two. That means that when I do the addition, the H is going to go on this side. And so this will happen, and this will happen. So the only product that we would get is this one. This doesn't happen. Now, why is it only that one? That's what we observe. We have done the reaction, and we only get the bottom product. So let me clear all of my ink here, because now my slide is going to do it for you. All right, so we can just cross this one off. So when adding HX, write in your notes, Markovnikov's rule. And make sure you know that. Because later on when we add water, water also follows Markovnikov's rule. Because instead of X being a halogen, X is now hydroxide. And we're going to add water in a little bit too. All right, so let's do an example here. I want you to follow Markovnikov's rule and tell me what the product of this reaction is. Now, remember that there are implied H's in some places, but not all. So, draw out the line angle structure, which is what I've drawn here. And then what I want you to do is add in the H's if you feel that you need to. And then answer the question, what is the product? Okay, so do the addition. I'll give you 2 minutes to figure this out. And I'm going to go see why my cat is screaming. I think she just wants me to pet her. All the time. All right, when you think you've got the answer, post something in the chat so I know. I know it won't let you post links, but you could just say something. Would the H go on the right side? I'm not sure what you mean by right side. Do you mean right side of the double bond? Draw out all the H's if you aren't sure. All right, I have some people that are done. So my hint, if you're still working on it, is remember what Markovnikov's rule is. The H goes with the most H's. One of these sides has one H attached to it. The other side is 0. Where could it go? All right, let's go over the answer. So I'm going to draw out the unwritten H's here. Let me get a different color. Let's do that. All right, so this carbon right here in the center of all of this mess has a double bond and 2 single bonds coming out of it to other carbons. That's already 4 bonds, so nothing's going to be added there. This carbon right here on this corner, oops, can have 2 H's coming out of it to make its octet. This one has 2. This one has 1. And that's all the missing H's. So now let's add HI. Let's do Makovnakov's rule. This H is going to go to the most H's. Well, in this carbon over on the left, there's 1. And this carbon on the right, there are 0. So this H is going to go here. And this I is going to go here. I break the double bond, and I break the bond that was between them. So I should get, this is my product. So I got a square, I got CH3, and I got I. And so that should be what it looks like, and there you go. Now, do you have to worry about stereochemistry? Like, do I need to draw one of these pointed up and one of these pointed down? Technically, you could just flip this over however you want to because it's symmetrical, so you wouldn't have to worry about it in this case. But for our purposes, we're only going to worry about cis and trans wedges if cis and trans are possible. So they only go on the double bond in other places. That's right. So remember, the double bond is all we are reacting with here. All addition occurs across a double bond. If addition could occur across a single bond, we would have covered it in the Alkynes chapter. But we didn't because that doesn't happen. Okay, so we have to have a double bond to do a reaction of this type. If you see just an alkane and I say alkane plus HI, the answer is nothing happens. But if it's alkane and double bond, then we do addition. You can show the H if you want, that's fine. Now remember, on a quiz, I can't actually have you draw structures because I'm not going to make you upload pictures. Like, that's too many moving parts in a quiz. Like, to have you take a picture of your answer, then upload it, and then if the upload does or doesn't work, like, I'm not going to make you do that. So, for the most part, you're going to be answering questions that are select from the pictures that I have drawn, or based on the picture, select the correct answer. There's going to be a lot of multiple choice in this class because I'm kind of stuck. Like, what else can I do? Short of having you submit your own assignment, which is kind of what the labs are for. All right, I'm going to give you 2 more. So I want you to predict the products based on Markovnikov's rule. Okay? So I have sort of drawn some of these out. You can see that as we go, I'm starting to draw these molecules out less and less and less, and we're just starting to use line structures. Here I've drawn some of the H's in, but not necessarily all of them, okay? So just keep that in mind, that not all of the H's drawn are the ones that are there, okay? Good luck. We're all counting on you. Now again, since you're drawing pictures, and I can't really expect you to put a picture in the chat unless you're like doing ASCII art or something, let me know when you're finished by just typing done. All right, we got a few dones in the chat. Let's go over the answers here. So, I'm going to draw out the implicit H's. So, there's an H here. But there's none here at this other junction because I already have 4 bonds. So, when I go to add my HBr, my H is going to go to the side that already has the H there. So, here's where my H goes. Here's where my Br goes. Kill off the double bond here, and then let's tidy up. So I got this structure, and I've got an ethyl and a Br. Should get something like that. For this bottom one, H has to go where the other H's are. Here's one H connected to this side of the double bond. No H is connected to this side of the double bond. So I'm going to put the H here, and the Cl here. And then let's tidy up. So this is a pentane with a methyl coming out of it, and then now it has a Cl coming out of it. And there you go. Now, if you are also drawing in these H's, totally fine. If that helps you to see what's going on. then that's good. Is there an explicit reason for the Br and the H going in those specific places? Yeah, it's Markovnikov's rule. Remember, the H has to go where there are already H's present. So this H was already there. So this is the H that I add. There's no H attached to this carbon. So the H won't go there. It chooses the side of the double bond that has more H's there. Can we do another one? Sure. I can just make these up. Let's see here. Let me get the chem drawer out real quick. And then I'll draw one here. I'll draw a few more. Give me a second. I'm just going to hit mute and I'll draw a few more. Okay, for some reason I'm having trouble trying to get this into Photoshop and not be super tiny. What if I just zoom in the camera here and then I paste it? Wow, this doesn't look good at all. Okay, so what I'll do is instead we'll just go to here. Let me get rid of this real quick. I'm just going to have to draw them because for some reason my ChemDraw program isn't pasting them correctly. So let me just go like this. So we're going to add H, ER, 2, doot, 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 doot. And then we're going to add HBr2, doot, 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 doot. All right. There you go. So for these two problems, tell me what the product is using Markovnikov's rule. All right, one more minute to finish these up. We'll go over the answers. I pointed out something in the chat that when you are writing out the names of these, so the format is that whenever you have a number, you want to separate out numbers from words with hyphens. And if you have multiple numbers, you want to separate numbers from other numbers with commas. I've done a bunch of these problems, but I don't know if I actually explicitly said that, so I apologize if that was unclear. All right, let's go over the answers. All right, so let me get the different color out here. This carbon right here in the middle, I don't know if you can see my cursor there. Here it is, right there. I'm dancing around. See? This carbon right here has 4 bonds to it. This carbon right here has 3 bonds to it. So there is an H here, but there's no H on this carbon. So when we add our HBr, the H should go with the other H's, and the Br goes in the other spot. And then we get rid of this double bond, and our new molecule should look like this. Doot, 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 Br. And so we would call this, and let's see what you have in chat. Yeah, that's right. So 2-bromo, 2,4-dimethyl, pentane. We'll do the same thing down here. Let's fill in the implicit H's. So there is 1 right here. And there's 2 over here. Where will HBr go? Well, there's 2 over here, but only 1 on that side of the double bond. So I'm going to put my H with the other H's, where there's most of them. And then Br will go here, and I get rid of my double bond. So now let's tidy up. We got this. That was what we started with, and then Br goes here. And so this would be 2-bromo, 3-methyl, butane. Got to synthesize all of the steps together. Now, if you're thinking to yourself, well, Chapter 13 quiz, what could Wes ask me to do? What I could do is give you a question that looks kind of like this. Would it be right if it was backwards? So, depends on what you mean by backwards. If you put the BR on this left side over here, no. The BR has to go on the side of the double bond where there are the fewest H's. The H goes with the most H's. Now, if you drew it like upside down, for example, like this, that's fine. Remember, conformations are okay. All we care about is that the connectivity is the same in both molecules that you drop. Now, what might you see on a quiz question? I might ask you something like, no, as in 3-bromo, 2-methyl. Well, if you have a tie in naming, like both directions go 2, 3, you put the 2 with the first one alphabetically. Remember that from the naming in chapter 12. So is it okay to not show the H? Yes, because H's are always implied. Remember that when we draw these line angle structures, we don't draw H's in them. Now, if you do draw it, then it's fine. So like if you want to put the H's in here that you added, and then there would be the other ones that were already there, that's okay. Just keep in mind when I'm drawing these structures as line angle structures, the H's don't appear, so you won't see them. Now, how might I test you about this sort of stuff on the exam? So let's suppose that I gave you this molecule here. Yeah, like that. And I might say HCl. And then I might say, what is the product? And then I would give you a list of molecules like this. 1-chloropentane, 2-chloropentane, maybe 1-chloro. I don't know, something like this. And you would have to do the reaction to get the correct product, which would be this. And then choose the correct name. Okay. Now, you would have to do this step entirely on your own, because that wouldn't be shown. I would just show you the picture of the reaction, and then you'd have a bunch of names to pick from. Okay? So, make sure that, one, you know how the addition reactions go with HX, okay? Make sure you understand Markovnikov's rule. And then, two, you gotta know how to name stuff. Naming is never gonna go away. Yeah, it should come together. It does take time, but you really have to practice this. And the best advice I can give you for that is to do the worksheet. Do the worksheet for chapter 13. Because you are going to see that there are so many naming problems. And I wish I could say it gets better, but chapter 14 is worse. The worksheet is like 17 pages long. It took me hours to write the worksheet for that chapter. So I hope that you appreciate it. All right, let's talk about water. Water is the exact same as HX. There is only one difference, and the difference is we need a catalyst to make this work. Without the catalyst, the reaction doesn't occur. So if I'm adding HOH across the bond, you can think of this as the X right here. This is our X. All right. I'm going to cover up the product here really quickly. We're going to predict the product based on what we see here. So how many H's are on the left side? 1. How many H's are on the right side? 2. So my H is going to go here. The OH is going to go there, and then I break the double bond. And so I should get something that looks like this. Doot, 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 doot. And then OH coming off of it. And there it is. Now, any group or any molecule that contains OH is called an alcohol. Now, you might be thinking, for various reasons today, that, man, I want alcohol. But we drink specifically one alcohol. That's ethanol. We'll talk about ethanol in chapter 14. But any molecule that contains a OH group sticking off of it that is also organic is called an alcohol. And alcohols are going to be the focus of chapter 14 because alcohols are very common, they're very reactive, and they do lots of interesting chemistry. For example, carbohydrates are like tons and tons and tons and tons of alcohol groups. All right, let's do more examples. So, just like before with HX, where X was a halogen, now do HX where X is OH. Now, as written on these slides, show me the products of the reactions, okay? Now, this is very important right here. There are no typos on this slide, okay? All right. So do these 3 reactions, and we'll come back and talk about the answers in a second. All right, a few more minutes to go before we go over the answers. All right, let's go over the answers here. So for question number 1, there was a comment in the chat. Hey, wait a second, there's the same number of H's on both sides. What do I do? And the answer is, well, let's draw out the H's first. Let's see what happens, what our products are. So if I were to put the OH on the left and the H on the right, I would get this. And if I were to put the OH on the right, I would get this one. And when you look at these, you should say, oh, those are the same thing, because all I do is rotate this one like 60 degrees, right? And then we're done. You could also name them. This would be cyclohexanol. We haven't learned how to name hydroxides yet, actually. So my suggestion to name stuff is probably not going to be super helpful. And this is also cyclohexanol, because the one position goes to whatever the only group is that's there, as we discussed in the cycloalkanes section. If you have only one group, you don't have to number it. So either of those is the same thing, so it doesn't really matter where you add it to, because you get the same result. So you should get this as your product. For the second one, I got one H here and no H's here, so this is just classic. Oh, okay, we're going to do Markovnikov and not have to worry about it. So my molecule would be doot, 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 OH, doot, doot. There you go. And then for the third one, we have one H and one H. So which side do I add it to? Uh-oh. Uh-oh. Something is missing. What's wrong with this picture? Dun, dun, dun. There's no catalyst. Nothing happens. So you don't have to worry about this stuff. Because if there's no catalyst, there's no reaction, right? What did we say about alkanes or alkenes in water? They're insoluble, right? You need that catalyst to help solubilize them and cause the reaction to occur. Now, generally speaking, we're going to be mixing these substances together really quickly to encourage the reaction to occur. Because water would just separate out from any alkene. Putting the acid in there makes it more soluble, but we still need to stir the hell out of it. But if you don't put the acid in there, no reaction will occur. What element is H2SO4? It's not an element, it's a compound. It's sulfuric acid. You need palladium, platinum, or nickel for H2, not H2O. Careful. Remember that giant chart that I recommended on Tuesday to write for your reactions? This is more of that part. You would want to put this on the giant chart. Water and sulfuric acid, but H2 is palladium, platinum, nickel. So you got to know those. You got to be able to remember them and then distinguish them. All right. That's it for that section. Hooray, we did it. Okay. What time is it? It is 12:51. Yeah, it's about time for a break. All right, so we've done all the addition practice. Next, we're going to talk about polymers. We'll probably finish the chapter today or get really close. So let me put this on the screen. You can keep asking me questions in the chat during the break. I will hit start the timer. Let me go get more Metroid music here for you. And we'll see you in a little bit. Oh, that wasn't very close at all, was it? Oh well. Let's turn the music down. Welcome back from your break. I hope everybody was able to get their water. We're going to continue our lecture with polymers. Woo, polymers. All right. Polymers are a very important category of molecules that are made by very simple means. And that means is we take double bonds and we react them with each other. And by doing that, we get an infinite chain of molecules called a polymer. Now, all plastic is a polymer. There are other natural polymers out there too, so like rubber and stuff like that. What you end up doing to make a polymer is you take a single unit with a double bond, and this is called a monomer. And what we're going to do is we're going to do an addition reaction using a double bond to add to another double bond. And so what we're going to do is we're going to take this double bond, and instead of connecting it over here, we're going to connect it over here. But if we were to do that, let me draw the intermediate here. So this would be CH2, CH2, which is now connected to this CH2, double bond CH. We have a problem right here in doing that. And so what ends up happening is that, wow, now I have 5 bonds to carbon. I'm not allowed to do that, so I have to undo something. And what I end up doing, or undoing, is this double bond, which I then pass to the next double bond. And then I have to undo that double bond and pass it to the next double bond. And so on and so on and so on and so on. And this happens over and over and over forever. And the result that we get is that we end up making a chain of these molecules that just keeps going and going and going on and on forever. And the result that we get is called the polymer. Now you can do this with any molecule that has a double bond. Now you need a specific catalyst to do this. I've left the word catalyst here. I'm not going to test you on what catalyst you need to know to do a polymer. We're just going to assume that polymers are catalyzed by some catalyst. Specifically, the catalyst that is working here is called the Ziegler-Natta catalyst. It's a very famous inorganic complex. And it's famous enough that I certainly don't remember it because I learned it in my 3rd year of college in 2008. I know it involves zinc. I forget what else it has, though. I can look it up. But the point is that when you expose ethylene to this catalyst, you polymerize plastic really quickly. And it's really cool to look at. So we can take any monomer, attach it to a duplicate of itself to make a dimer, and then a trimer and a tetramer, and so on. And then once you get tons of them, you have a polymer. Now, depending on which polymer you use, we used ethane, or ethene in the previous example. The common name is ethylene. But you could use anything with a double bond in it. So, for example, that's all that we have here for this reaction. I could use this molecule. This is propene. And if I attached it to a second one, what would happen is I would move the double bond over here, and then I would move the other double bond over here, and so on and so forth. And what I would get is something that looks like this. And this would be polypropylene. Each of these individual monomers is propene. If you've ever had a styrofoam cup, styrofoam cups are polystyrene. Styrene looks like this. It has a phenyl group. We're going to talk about phenyl a little bit later. But you can imagine it does the exact same thing as propene, and it does, except instead of having these just CH3 groups at the end, each of these CH3s would be this sort of ring thing. That's really all I have to say about polymers, is that, hey, if you take double bonded molecules and you string them together, you make a polymer. Your task will be to identify what a polymer looks like based on its reaction. So if you can look at this and go, oh, okay, I see how I got from one to the other, then you're in good shape. All right, that's all I have to talk about for polymers. Here are some more examples of polymers. Plastic, rubber, nylon, Kevlar. Nylon's a really fun polymer because the way that you make nylon is to combine two chemicals that are insoluble. But the chemicals, despite being insoluble, are very reactive with each other. So you pour one and then you pour the second one on top of it. And at the interface where the two layers touch is where the nylon forms. So you stick like tweezers in there, and you can pull the nylon out from the solution. And it just keeps coming out until you run out of one of the chemicals. It's really cool. If you want to see that in action, you just go to YouTube and type in nylon synthesis. There's many good videos on that. All right. What kinds of molecules do we study in organic chemistry? In fact, let's write that on the slide here. What kinds of molecules do we study in organic chemistry? Anybody know the answer to that question? Carbons and hydrogens. True. Anyone else want to take a guess? Oops, that's not what I meant to do. Organic compounds? The correct answer is we study all kinds of molecules. Yeah, that was about where I thought that pun was going to go. All right. What's an alkyne? An alkyne is any hydrocarbon that has a triple bond. You did laugh out loud. Okay, that's good. At least somebody laughed. All right. Any molecule that has a triple bond in it is called an alkyne. And alkynes are not... Excuse me. Press F to pay your respects. Thank you. Please like, comment, and subscribe. I'll be here all quarter. All right. Triple bond, alkyne. There is really nothing exciting or new about alkynes that we haven't done. The only thing that's really unique about alkynes, you can see by their shape here. And I don't have a vertical highlighter, but that's okay. I guess I should highlight all the way down there. Is that when you have a triple bond, you get this really, really, really straight arrangement. And the reason for this is because that when I have a carbon, let me draw on my carbons here. So carbon, 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 carbon. So I got H3 over here. There are no H's on this carbon. There are no H's on this carbon. This one is H2. When I have only two electron groups connected to a single atom, the arrangement I get is linear with a 180-degree angle. So not only is the triple bond itself linear, but the 2 carbons coming out of it are also linear, because they have to be. So you get this really long and straight part of a chain that has a very particular geometry to it that is distinct. Now, remember that we said, when we were talking about alkanes in the previous chapter, that alkanes have low boiling points, but if the alkanes themselves are unbranched, that is, they have a linear represented chain, their boiling point is higher than if it's branched. So like something like this would have a higher boiling point than something like, say, this. Okay? And that was because the surface area was more elongated and flat. With alkynes, you definitely have this elongated and flat part. So the boiling point of these tends to be a little bit higher. And the longer and straighter it is, the higher the boiling point is. All right. How do you name alkynes? Exactly like you name alkenes, except you add "-ine" instead to the end. So let's do an example here. And if you're looking at this and going, wait a second, that looks weird. Yeah, it does. We'll talk about that in a second. How would you name this alkyne? Well, if it was an alkene, we'd try and put the or the double bond at the lowest number. We're going to do that same thing for the alkyne. We're going to put the triple bond to the start of it at the lowest number. So this would be 2, 1, 2, 3, 4, 5 carbons would be pentane, but it's an alkyne, so we call it pentyne. There you go. And again, I drew the structure wrong on purpose because sometimes I might try and hide the fact that it's an alkyne from you by drawing it incorrectly, and then I'll mention, wait, the structure's drawn wrong. Can you draw it right? So on a piece of paper, scribble down what the correct structure should look like for an alkyne. Remembering that the triple bond itself is linear, and then everything connected to it has to be linear too. So what would that look like? And hopefully what you drew was something like this. So 1, 2, 3, 4, 5. Hello, Maya. She's in the background going, meow, meow. I'm trying to teach her to say hello. But I don't really want her to practice right now. All right. Here's some more alkynes. Is there other stuff on the next page? Okay. I want you to name the following alkynes while I go console the cat again, because apparently 10 minutes have passed, so I had to go pet her again. Remember, name them just like you'd name alkenes. Find the longest chain and include the alkyne in that. Okay? And then name the groups. So I'll be right back. All right, how are we doing on naming these? I've petted the cat, and then I put her in the laundry because she apparently wanted to go in the laundry. Then she didn't want to go in the laundry, so I picked her up, and now she's staring at me in the hallway. Yeah, you were. Let me know if you need any help. One more minute to go before we go over the answers. So when you're numbering your chains, make sure you're numbering through all the carbons. For the first one on the left here, this is the first carbon, right? So this is going to be 1. Try and work from there. All right, let's go over the answers. So I'm going to number the longest chain, which I can get to here, and then it doesn't really matter which way I go. The longest chain would be 4. Group 3 would be methyl, so I would have 3 methyl. My triple bond starts at position 1, 1 butane. Over here, same thing. So I have to include the alkyne in my longest chain. 1, 2. That's going to be the shortest way to get to the alkyne. So we're going to start numbering here. 1, 2, 3, 4. Where do we go? Well, this would stop at 5. I can get 5, 6 in the other direction. So I'm going to do that. Here's a methyl. Here's a methyl. 4, 5, dimethyl. And then the triple bond starts at carbon 2, 2 hexyne, because it's a 6-carbon chain. All right, there you go. All right. Any questions? Let me know. I think the questions that are in the chat right now, those were answered through these. But if those are for a different question, let me know. All right. Now, I don't really have that many examples for these. What this slide is just saying is that because alkynes are basically like alkenes, they just have 2 extra bonds available. They follow all of the same rules that alkenes do, but the first addition only gets rid of one of the bonds. So if I start with an alkyne and have a triple bond, and then I add to it, I get a double bond and whatever groups I added. And then I could add to that again a second time. So you can do addition twice. Now, alkynes follow the Markovnikov rule also. So if I do HX, I will get a result that is consistent with the Markovnikov rule, just like with alkenes. So let's examine some of those problems here. So let's suppose that I want to add H2O to my alkyne in the presence of a catalyst. So let's go to the problem viewer here. And look at that. So let's go to this. Oh, that's not what I wanted. Hold on. Don't know what happened there. Okay. Okay. So we have a triple bond, and then we have a single bond, and then we have that. We're going to add H2O, so I'm going to add HOH, and I have my catalyst present. So I have that, so the reaction does occur. So let's add water to this. Now, where are my H's here? So this carbon right here, and this carbon right here, are my triple bond. There are no H's on this because I already have 4 bonds coming out of it. The triple bond and then the other single bond going over here. Right here, I have an implied H, which isn't drawn. Because there's only 3 bonds coming out of that carbon, right? So when I add my water, my H is going to go over to this side. And then what I'm going to get as a product is I'm going to get a double bond. And then the ethyl coming out of it. And then the OH is going to go right here. Because the H went over here, right? So there's 1 H, 2 H's that are there now. And then if I wanted to add water to that one, I do the same thing. Which side has more H's? Well, clearly it's this side. It's already got 2. This side still has 0. So adding a second water will give me this as my molecule. And there you go. So with that in mind, what I want you to try and do, I want you to tell me the product of this reaction here. So I showed you how to do it with H2O and a catalyst. I want you to do it with Cl2. Tell me what the product would be once you're done, and then try and name it. Because you should be able to name it. It's only going to have chlorines in it. Okay? Try that. I'll give you 2 minutes to do it, and we'll go over the answer together. All right. Do we have the answer? So let's draw our alkyne. Do, 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 do. Do, 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 do. And I'm going to add Cl2 to it. So Cl is like that. When I have X2, I just add across the double bond. So this chlorine is going to add there. I'm going to break and break. And I said double bond, but what I meant was, in this case, it would be the triple bond. But for alkenes, it would be the double bond. And so the result that I would get would be double bond is left. 1, 2 carbons. And then each end has a Cl on it. So Cl, Cl. And then now I have to add another Cl to it. How would that happen? Well, same thing. This goes here. This goes here. Break this double bond. Break that bond. And now I would get a butane. Here's the old Cls. Here's the new Cls. And so the molecule I would get would be 1122 tetra. Let me fix that E here. Tetrachloro butane. There you go. Yep, there's 2 Cl2. So I did, here's 1 Cl2, and then there's the second one. That's not a trick question. That's called chemistry. We're balancing the reaction. All right. You want a trick question? Here's the trick question. What's the result of this product? You should immediately look at that and go, uh-oh. What do I do? What's the answer to this one? I'll give you a hint. No catalyst, no reaction. So yeah, if there's no catalyst, nothing happens. Let's suppose I did this. I'm going to add that in there now. Now what would the reaction be? Draw the product of that reaction, now that I've edited the catalyst into the reaction. And then name the product. All right, have we found the product? It's totally just butane, that's right. Let's show how, oops, I don't know what I just deleted. There we go. Let's show how you get butane out of that. So, doot. We're going to add H2 with my palladium catalyst. Or my palladium cat. Oh no, I said cat, Maya heard me. What the hell was that sound? Maybe she really did hear me. I hope that she didn't just knock something over on top of herself. I'm going to add H2 across the bond. Break one of these, break that. They're H's, so I don't have to draw them. I'm going to add another H2 across the bond. There are H's, I don't have to draw them. Hooray! It's the simplest molecule. So you can turn alkanes, or sorry, you could turn alkynes into alkenes and then alkanes by hydrogenating them. All right. So alkynes are nothing new when we consider all of the stuff that we learned about alkenes. H's go to the one with the most H's. That's HX. This is H2. H2 adds across the whole bond, H on both sides. So if I was doing HX instead, then I would have to add it in this direction. And I would get that as a product. But this is just HH. I have to put one thing on each side anyway. So it doesn't matter because it's symmetrical, right? Can I put both of them on the same side? No, that's not how addition works. We add across the double bond, so I have to add something to each carbon. My Photoshop broke. That's okay. There we go. That's right. Yeah, H2, you just go across the double bond, one on each side. Same with Cl2 or X2. We're always putting one thing on one side of the bond and the other thing on the other side. What those things are depend on what the molecule is that we're adding. And if it's HX, we have to follow Markovnikov's rule. I don't know what you mean by monogamous bonds. If you mean just like one element, then yes. All right, so there's our answers. Let's do the last section. We're not going to finish this today, but we'll get close. How much time do I have? I have 10 minutes. Okay. So I want to talk about aromatic compounds. Aromatic compounds are the last type of hydrocarbon that we're going to cover in this class. After this, we're going to start adding in extra elements. So we're going to start with oxygen and then sulfur and then nitrogen. But for now, just C's and H's still. When you hear the word aromatic, you might think, oh, it must smell weird, or smell good, or smell at all, right? And that's usually true. Most aromatic compounds smell nice and are produced for that purpose. So, for example, like oil of wintergreen or vanilla, these all have aromatic components to them because they smell good. Now, what causes that smell? It could be a whole bunch of things, but what is in common with all aromatic compounds is that they have a specific feature to them. And that feature is this. This is called the benzene ring. So a benzene ring is the feature of an aromatic compound. It's this whole ring right here. So the whole guy. And what this is it is alternating single and then double bonds. Single bond, double bond. Single bond, double bond. And then when we don't draw in the hydrogens, you just get this shape right here. This is a very distinctive shape. I'm certain that most people have seen this before. I've been told that benzene smells good. Like it smells kind of sweet. However, benzene is a carcinogen. Don't breathe it. I remember in college, I told somebody, I've never smelled benzene because I know it's a carcinogen. And they're like, you've never smelled benzene? Here, come try some. And then they chased me around the lab with a bottle of benzene. That's something I did in college. I ran away from a grad student who was chasing after me with a bottle of benzene. That is a thing that we did. All right. Now, aromatic compounds are compounds that contain benzene. So if the molecule has this structure in it somewhere, it's considered aromatic. If a compound does not have any benzene rings in it, we call it aliphatic. Aliphatic is just basically the opposite of aromatic. And so you can call an entire compound aliphatic, or you can just call part of a molecule aliphatic. So an aromatic compound might have an aromatic part and an aliphatic part. We'll show some examples of that on the next slides here. Now, in alkanes and alkenes and alkynes, when you change the bond order, so from single to double to triple or whatever, within a molecule, those bonds have different lengths and strengths. That's sort of beyond the scope of this class. But experimental evidence suggests that benzene rings have all of the bonds are actually identical. And so what that means is that even though I have the double bonds in these positions, I could say that the real structure is sort of the average between these two. And so the term for this is just that we say that the double bonds are considered to be delocalized. In other words, there aren't just 3 double bonds in benzene, they're sort of everywhere. And so that's drawn like this, as this little circle deal. So the only reason that I really bring this up, because you're not really going to care about the fact that benzene is delocalized, is that you may see this structure written in places. And it's important to note that if you see a hexagon with a circle in it, that's supposed to represent benzene. Why does it represent that? Because these double bonds can move around. Remember how with polymers I could move a double bond to make a new bond? And then that would kick out the other one, and then that would kick out the other, and so on and so forth. With benzene, that's what's happening. I can just move the double bonds around however I want to, and so they're mobile. They're delocalized. If they were localized, they would be stuck in one location. But specifically in benzene, they aren't. And that's neat. Now, because of this, since it's hard to really pin down where the double bond is to react with, benzene's not very reactive. So even though there are double bonds in benzene, benzene rings don't react with stuff unless you have special catalysts. In the lab that you're going to do next week, for the hydrocarbons lab, you're going to talk about a molecule that has benzene in it. It's toluene. In order to react with toluene, we need a special catalyst for specific conditions. Okay, so all of the reactions that we've talked about so far, so like H2, X2, HX, if you try and react them with benzene, it doesn't work. Okay? You can't add H2 even with platinum, palladium, or nickel. It doesn't work. Can't add X2, it doesn't work. Can't add HX, it doesn't work. We need a very specific catalyst to do that. That catalyst is usually something like aluminum trichloride or something like that. But we're not going to do those reactions anyway. So if I give you a reaction such as, say, let's just leave that on the screen for this part of the discussion. That's chem dry. I don't want that. So if I gave you, say, like this reaction, so I have a benzene, and then connected to that is a double bond, and I said, what's the product? The product that I want you to draw is to say, okay, well, benzene doesn't react, so it stays the same, but this double bond on the top will. And so the H2 would go onto this double bond here. But the benzene part is unreactive. Okay? So keep that in mind. Benzene rings don't react. They're going to be stable. All right. Now, whenever you see benzene, anytime you have a benzene ring drawn, oops, that's the wrong pen. There's always one thing connected to the outside part of it. So if this is my benzene, yeah, it looks kind of like a face. I can have one group on each carbon, because otherwise I would have more than 4 bonds. Now, those groups could be H, or they could be other things. So, for example, I could make this Cl, or I could make it CH3, like I could do this to it. I could do any number of groups off of my benzene. But I can only ever have one out there, okay? I think on the next few slides, yeah, here we go. Here are some examples of different types of compounds that we can have and their names. Remember that because position 1 for a cyclic compound, oops, not 2, what am I doing, is always where the only group ends up. We don't have to put a 1 in these. But if we had multiple groups coming off like this, we could. The other thing to note about benzene is that if we look at the geometry of these molecules, so these are all, so if I draw this H here, I have 1, 2, 3 electron groups around each carbon, so that the geometry of each of these is trigonal planar. So if I go into mol view, let me get mol view up here real quick. And I need to draw a benzene really quick. Oh, there's a template for that. Or template for that. There we go. And then we'll tidy up. And then we'll 2D to 3D. And then I will capture mol view. Alright. Alright. So I have drawn both... Oops. Benzene here and cyclohexane. Remember how cyclohexane, these are all tetrahedral. Oops, I didn't mean to do that. These are all tetrahedral, so they have 4 things coming out of them. You can see on my cyclohexane molecule that it occupies 3 dimensions. But if I look at the benzene over there, you can see that it looks very flat. And that's because all the carbons are trigonal planar. So benzene rings are very flat. Cyclohexane is very puckered, like it zigzags around. Cyclohexane is not flat at all. Okay? So even though they look the same on paper, in fact, if I turn off this, they look really similar when drawn as line angle structures. You got to remember the geometry. And note that these are very, very different molecules. And let me rotate those around so that they match up with what's on the top here and what's on the bottom. Okay? If you're ever in doubt, draw it in mol view and spin it around. All right. So we're just naming groups off of the benzene. Here's some new groups that we haven't seen that are going to start appearing. So we got the nitro group. A nitro group is NO2. You might have heard of something called trinitrotoluene. On the next slide, I'm going to show you toluene. You could probably imagine what trinitrotoluene would look like. These are other molecules that are so common that they get common names. Or trivial names, I guess is what I read on here. So toluene is benzene with a methyl group on it. Phenol is benzene with an alcohol coming out of it. Aniline is benzene with an amine group on it. We're going to talk about amines in chapter 15. And then benzoic acid is benzene with a carboxylic acid. We're going to talk about that in chapter 14. So this is chapter 14. And this is chapter 15. So yeah, more groups are coming. It's only week 3. We have 7 more weeks of groups. That's not true. We have like 4 or 5 more weeks of groups, and then we just start doing crazy stuff with them. I don't know how much more I can really cover in 8 minutes. Hold on, let's see where I'm at. Yeah, I don't want to do these exercises today because I think it'll take more than 8 minutes to name these molecules. So I'm going to stop here with these basic groups that you will encounter in organic chemistry with benzene. So it's best to have those committed to memory at some point. You can always reference them, of course. However, that said, I'm going to refer to them by name, and if you have to keep looking up, oh, what was phenol again? Every time, then that's going to eat up your time while I keep lecturing. So now I do realize you can always just pause the video and go back in time and go forward in time or whatever. That's totally fine. I believe that will be it for this week then, because we don't have a Thursday class. So go out and enjoy Inauguration Day. Have a hopefully more relaxing weekend than the past few weeks have been. Make sure that you study chemistry. And also make sure that you turn in lab number 1 by tonight. Quiz number 1 is due Friday. An email will go out on Friday and Saturday to announce that for last call. Beyond that, really, I don't have much else to say. So I hope that everybody has a wonderful weekend. And we'll see you next week. Have a good one.